So good afternoon. Today we have Tim O Leary from Cambridge. So Tim did his undergrad and master studies in mathematics and pure mathematics. Then he started a PhD in algebraic topology, I think. No.
Hyperbolic geometry.
In hyperbolic geometry, and almost suicided himself. and so he switched to electrophysiology. He's found the good path. He had a vision. And then his PhD was in Edinburgh, and then he was postdoc in Brandeis in the US, close to Boston. And now he's lecturer at the University of Cambridge in the engineering department, working on basically, theoretical, broadly saying, theoretical approaches to neuroscience. And
okay.
Thanks.
Thank you, everyone. I'm going to begin with a brief story about some recent work, which is a collaboration with some experimentalists. We didn't do the experiments. All we did was analyze some of the data. And I'm going to motivate the rest of the talk. In particular, I'm going to explain what I mean by degeneracy in this context, using this as an example. Okay? So let's start with something concrete. Here's a task. And it's a task that even an animal as stupid as a mouse can solve. Okay? So we have a maze, and at the start of the maze we get shown a color, and depending on the color we need to turn left, we turn right. Okay? And mice can learn this very well. They can learn it so well that they can actually perform this in a virtual reality environment. So where they're on a ball, they're running along, and one projects a virtual maze. And I'll show you an example of that in a moment. That's a technicality. It makes some things easy to do. But this now is just some behavioral data showing that after so what's missing here is the learning phase. These mice would maybe take 2 weeks to learn this task. Once they've learned it, though, over many days, an entire month, they can make the correct decision almost 100% of the time. So they're very good at this. And one thing that we might be able to say is that their brain has represented this environment. It has a good representation that allows the animal to make a plan and solve the task. So, where is this representation being built? Well, the answer is we don't really know, but clearly it must involve something to do with sensory inputs and something eventually to do with motor outputs. And this is a map of the rodent brain. And there's a part of the brain called the posterior parietal cortex, the PPC, which is kind of in the middle of the sensory and the motor regions. It's mixed in with everything. And to summarize a lot of work, this is a kind of abstract representation area. It's where you make a diagram of the task ahead of you in your brain, perhaps. So we could make a cartoon like this, and we could say, okay, the PPC is the circuit. It interacts with some other circuits to generate some motor output. And it's informed by sensory inputs, again, via other circuits, but it's in the middle of all of this stuff. Does not have direct contact to the outside world. So it's like the homunculus, the man buried inside your brain. Okay? So here's what the experiment looks like. On this side, this is a mouse, you'll see in a moment, on a little ball, and he's navigating inside this maze and can turn around and so on. And the advantage of this is it allows our collaborators to record from individual neurons. And these neurons have a calcium indicator so they can see when the neuron is active. And this is what it looks like. The mouse is running along. It sees patterns on the wall, and it makes a decision based on the pattern, left or right. It's gone left. Got it right. It's teleported back to the start, and it does the task again. And this is now showing the activity of the brain in this particular region. Okay? So this is very powerful because it allows us to take a high-dimensional time series of the activity during the task and correlate what's happening in the brain with what the animal is doing. So that's what this looks like. Here we have many time series for hundreds of cells, in fact, and each of these little blips is when the cell gets excited. So now we can ask, how can we decode what's going on in this part of the brain. And one observation, which was made again by our collaborators, is if we represent the task, here's the start of the maze, here's the finish of the maze, and we sort the neurons by when they get excited, what we find is there's this nice kind of continuous tiling of the task from start to finish. We can find a neuron that's excited somewhere, okay? So in this sense, we can say, yeah, well, there's a map between the task and the activity in this part of the brain. If we keep this mapping, in other words, if we keep neuron 1, neuron 2, neuron 3, etc., and now we say, this is how things look on day 1. What happens if we now look 1 week later? The animal still performs the task very well, perfectly. It needs this part of the brain to perform the task. So it makes sense that 1 week later we should see this map again, if it's using the map. But we don't quite see that. So after 10 days, this map kind of disappeared. After 20 days, very little evidence of the map. So it's fair to say that the activity represents the task, but the representation is changing, is drifting over time. Even though the animal is not apparently learning anything, it's doing this task very well. Now if we went to day 10 and we rearrange the neurons, maybe select different ones, we can find the representation again. But now if we keep this basis essentially and we go back, we've lost it again. Okay? Does this make sense? So it's like there's this kind of mapping between the task and the activity of the neurons, which is for some reason moving slowly over many days. And this is strange because if the mouse needs this representation to solve the task, how is it accessing the representation if it keeps moving? I mean, it's kind of a strange thing. Okay?
Was the distribution of firing, well, the equivalent of the firing rate that you have in here, was it the same across?
Yeah, so the average firing rate does not change. Yes. Some neurons become more excitable, some less excitable, but there's no clear pattern. It's not just that some of them all just kind of go quiet. No. 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 Okay. So we asked a very simple question. We said, okay, this looks like a mess, but there's hundreds of neurons here. What's the simplest way that we can go from the representation in the brain to extract a variable in the task? Can we figure out where the animal is, which way is turning, how fast it's running, just from this activity? And thinking for a few seconds, you should say, yes, surely, there's a map, okay, between these things. So here's what we wanted to do. Here's a trajectory, and let's say we take position on the track, and we've got the time series of all of this high-dimensional vector of activity. We bin in time, so we index by k, where k is some time bin, and we want to decode this variable from this variable. What's the simplest decoder we could think of? Just a linear mapping. So we're just going to say position is just some weighted sum of all of these activations. Okay? So is this going to work? Answer is yes. Works very nicely, in fact. So this is just using least squares. You take some test data from a day, a few of these trials. You fit your coefficients, and then you take some data that the decoder never saw on the same day, and now you decode the position of the animal just from the neural activity, and it works quite nice. Okay? And you can do this for speed, you can do it for angle. So you can recover essentially the state of the animal from the neural activity. And you may ask, okay, why a linear decoder? One reason is that it's simple. Another reason is that actually neurons and circuits, they perform weighted sums, right? This is what they do to an approximation. This is a neuron. It takes weighted sums of activation of other neurons, and it produces some kind of output. Of course, there's some non-linearity here. We're ignoring intrinsic dynamics of these neurons, but to some approximation, this blob could be a neuron, could be a circuit. It's not so bad. So this is to say that this linear decoder, you could argue, is a biologically plausible decoding rule. If we were to think about these bits of the brain that need to access information here, then they could do a weighted sum, okay? Okay.
Did you try to get the decoder with variance matrices?
We didn't, no, nothing clever. Very simple, very, very simple. We can do better if we know something about the relationship between the neurons, of course, yeah. But we're assuming that from the neuron's point of view, it can't do anything fancy. What it can do is maybe change these somehow.
And were there any distinctions between neuronal types, or
No,
what
nothing. Excitatory neurons. Yeah.
Oh, so it was just exciting.
Yeah. Sorry. Yes. It's yeah. Okay. So if we now take this decoder, we find these coefficients m. We have now a nice readout. The next question is, because this representation is drifting, evolving, this decoder at some point not going to work, right? So let's see what happens. Here is like day 0, in the middle of this training, several weeks performance of the task. If we look on the previous day, we can still decode, but our error is increasing a bit. If we go 5 days in the past, it's looking a bit bad. And similarly, if we go into the future, it's not looking so good either, okay?
In this view, the coder is the decoder and
Yes.
the line is the mice.
Yes,
Okay.
yes, sorry. So the solid trajectory is the actual trajectory, and this one is the decoded trajectory from the activity. So we see this kind of gradual degradation of the decoder over time. And that's what this looks like if we plot, say, the mean squared error or the percentage difference in the predicted location. Then on day 0, where we've trained our decoder, we have low error, which is good, and then it's symmetrically almost degrades. This makes sense, right? But this is a population of many hundreds of neurons. In fact, to do this decoding, we don't need all of them, okay? Many of the coefficients are small, and we can enforce, say, a sparse decoder if we want, okay? This also raises the question, if instead of training on day 0, why don't we take training data on day 1, day 2, day 3, day 4, etc., and fit a big, well, not even a big model, but a model using data from all of those days, and test on all of those days. So we could think of this as a concatenated data set, okay? Is this possible? In fact, it is. The concatenated decoder does not do as well as the one that's fitted to a specific day, but it certainly does much better and doesn't degrade over time by definition. So what does this mean? It kind of means that a linear decoding of the population activity works reasonably well. So weighted sums work reasonably well. But there's sufficient degeneracy and redundancy in the representation that we can find a linear decoder, a weighted sum of these activities, where the drift is in the null space, or close to being in the null space of this linear decoder. So one that's almost drift invariant, okay? Now, I've kind of waved my hands and said a linear model or linear decoder is kind of something that the brain can do. And maybe on one day it could adjust its weights and keep them at some value. But how could it find this drift invariant space? Okay? It can't measure what's going to happen in the future, what's going to happen in the past, and come up with some nice drift invariant decoder. It will have to do things in real time. But what this concatenated analysis shows is that at least in principle there's something close to an invariant subspace. So then we actually just took one of these linear neurons, and I'm not going to go into the details. It took a very, very simple Hebbian learning rule where you just take the error, the immediate error on any time point, and you adjust the weights in real time. And this is showing the decoder performance just in 4 trials. It's doing okay. After many tens of trials, now the decoder is much better, in fact, than any single fixed linear decoder. This shows how the error goes over many days. It asymptotes quite quickly. But the important thing to take from this is that the average change in the weights, because there's weights to many, many hundreds of neurons, is tiny. So this decoder can compensate this drift by just making tiny adjustments to each of these synapses or the weights that are there. And the only thing it needs access to is the global error, the global performance. And the global error could be something like, I made a prediction, I think I'm here, my sensory information tells me no, so that's some kind of error with a sign. If we feed that back to the neurons, they can do something like this. Okay. So in summary, the neural representation of these familiar tasks is not unique, it's changing, and in fact it does continually evolve. So this tells us already that the representation is degenerate. There's redundancy in this part of the brain, probably in many parts of the brain. And this is not a disaster. This isn't some massive paradox that makes all of neuroscience fall to pieces. Just a simple feedback rule can compensate for this drift. So yeah, the brain might be able to function in spite of this drift. And the thing that then completes this picture is that, of course, the PPC and the rest of the brain is acting. There's motor output and there's sensory input. The thing that connects them is the world, is reality. And it's the world that's giving this error signal. And maybe this error signal doesn't come from the world directly into the brain. The error signal needs to propagate through these other circuits. These circuits are making predictions, and in a sense the circuits are comparing their predictions with each other and propagating error. So one, if you like, assumption or prediction of all of this is that all parts of the brain should be sharing error signals all the time. We never stop learning, even when we're not learning anything new about the world, even when our behavior is not changing. Okay? So, that was the end of part 1. And as I say, this is just our sort of early stages of this project. And it sort of inspired some of the questions. In particular, we're now comfortable with the idea that the representation of more or less anything that the brain could learn is probably redundant or degenerate. Why? The standard answer is, if you lose a neuron, you don't want to forget everything, okay? So you want to spread your information across many neurons. Another answer is, biology is messy, it can't precisely tune everything, so maybe you want many attempts at tuning the same thing, okay? And that's actually sort of closer to the findings that we made in this next part. We explicitly wanted to say, what if we have a degenerate network? How does this affect the ability of that network to learn? So, to tackle this question, what we needed to do was to set up a very general theoretical framework, okay? So this is something which we saw in the earlier slides. We've got this idea that this network somewhere in the brain. It's somehow involved in doing a task, and it must be receiving error on this task. And the thing that turns the error into a parametric change in the network is a learning rule of some kind. This should be quite familiar to most of you who have a neuroscience background or are neuroscience curious. So this is what we should have, that if learning is occurring, our error is decreasing over time. End of the story. And possibly this feedback may be not continuous, it may be intermittent. We maybe only get feedback occasionally when we make a mistake or something like that. So it could happen at discrete time points. But biology isn't perfect, so this learning rule is not going to be perfect. There's going to be some noise here. The error signal may not be perfect, the way this turns into a learning signal, a plasticity signal, may not be perfect. In addition, and I'll define this more carefully as we go, the rate of change of the parameters may not be perfect, is subject to noise, but also the parameters themselves could have independent noise, right? If any of you have studied synaptic physiology or looked at papers describing the micro neuroanatomy of the brain, you see these synapses coming and going all the time. It's very dynamic, and some of this seems kind of random. So it's reasonable to expect that the connections have an intrinsic noise source that's independent from learning. It's just a nuisance. And the way we want to address the question of how network size influences learning performance is we want to change network size. So the way we do it is simple. We take our neuron, our network, and now we're just going to add neurons and synapses. Keep the same inputs, same outputs, but add stuff in the middle. And this will make us a bigger brain, in a sense. Okay. So next question is, we've had this very abstract thing, okay, there's some learning rule. What kind of learning rule do we want? We actually don't know what learning rule the brain uses. There's lots of theories out there, but we want the analysis to be kind of general. So actually, what we'd like to do, we'd like to consider all possible learning rules, okay, in quotes. So how are we going to do this? This seems a bit much to ask. So we put a condition and we say up to first order. So what does up to first order mean? Well, going back to this picture, if we decreased error over time, and we did this by changing connections, trivially what this means is that the error at time t was higher than the error, was lower than the error at time 0, right? This error function must have decreased over this interval. So what does that mean? Well, just by the fundamental theorem of calculus, that means that if we were to look at the gradient of the error and look at the dot product of the gradient of the error with the trajectory that this synapse vector follows, this, if learning has happened, must on average have been negative. We should have been pointing down the hill, on average. Not at every point in time, but on average in this t interval. Okay? So what we can say then is this thing is equal to t times the expected value of this correlation of the gradient with the direction that the synapses are changing. Okay? So it doesn't matter what the learning rule is. If in the interval t we got from a high error to a low error so that this is negative, it means on average, it's almost a tautology, the gradient must anti-correlate with the direction that the synapses are moving. Okay? But biologically, who knows? Maybe synapses can compute a gradient. I don't think so. I think computing an explicit gradient is very difficult because every parameter, the error depends on the relationship between all the parameters. So very, very hard to imagine how the brain can compute this. But if it somehow manages to learn, it must, this anti-correlation must hold on average. And it's possible that a biologically realistic learning rule could actually have quite a weak anti-correlation. So a bad learning rule could have an arbitrarily small anti-correlation. A good learning rule would be one that follows the gradient precisely. So this allows us to parameterize the quality of all learning rules by saying the best one is the one that follows the gradient and the worst one is the one that has nothing to do with the gradient and you don't learn. Okay? So you may ask, how can we have a learning rule with no gradient in it that's kind of biologically plausible, but where you get this correlation? Here's an example. If we have some synapses and these are doing things locally. They can control their weights, they can store information, maybe with errors, and they're subject to some kind of global error signal. This could be something like a dopamine hit, or something that we get when we get the answer right to something, some kind of error signal. What's a simple mechanism that can allow learning? Well, here's one. Suppose my weights, my synaptic weights are just changing, so that in some time interval tau, my weights increased. If at the same time my error increased, that's bad, okay? If, however, the error decreased, that's good. So what should my learning rule do? It should say, if this happened and this, reverse the synaptic change, or don't take it, erase it. If this happened, keep it. So one way to implement this is to simply put a condition on the sign of the change in the weight, which looks like this. Here's the delta W, the change in weight. If this was positive and this was positive, that's bad. So make the weight change the opposite. If this was positive and this was negative, that's good. Okay? And again, multiplying the signs will give you something consistent. But just to convince you this works, if we just take some error function, this is just something which I made up, which I make depend on a parameter W, and we want to get here, we want to minimize our error. If you implement this, this is what a trajectory looks like. It's making these random perturbations and reversing or keeping the sign depending on the change in error, and over time this thing spends more time in the region of low error. But it's not explicitly computing a gradient. All it needs to know is what the error was in the past and roughly what the weight change was in the past. Okay?
And how is the error computed?
The error by a prediction. So my prediction is I'm walking and I think the table's over there, but my sensory information tells me no. I get a surprise. The surprise perhaps releases some kind of neuromodulatory signal or explicit error signal, and the part of my brain that told me the table's not there receives this error. So it needs some kind of way to encode this signal biologically with the sign, but I think that's reasonable. Okay.
What's noise here?
So the noise here is coming from the fact that in this case, in order to learn, I have to do a random perturbation.
Okay.
So I'm just doing perturbations all the time. And in fact, this is a very, very bad learning rule. It doesn't approximate the gradient very well at all.
Excuse me, did you apply this paradigm to the run training? I mean,
You could.
You guys analyze
You could.
the error trials?
There are very few.
They were
We don't have the data, so our collaborators are now gathering data during the learning. So for practical reasons, what they used to do, they take the animal, train it without doing the measurement. They just put it on the ball, leave it for 2 weeks, and they measure the behavior and say, when they're good enough, now we put them on the microscope and measure.
Yeah, but in fact it would be nice to have like a task
Yes.
that rises
Where there's errors,
errors.
yes. And indeed, that's something that they are now designing, yes. Yeah, but we didn't have that. Okay, but anyway, that learning rule was just to say that, yes, we can have this condition being true without knowledge of the gradient. Okay?
Why does f increase back again in your...
Oh, so this is just sorry, it's not a function of time.
Okay.
It's a function of space.
Okay.
Yeah. I'm just making f depend on the value of w.
Okay.
Yeah. I'm parameterizing it by w, and I want, yeah. Okay.
So just to understand, so you have W changing sometimes randomly,
Yeah.
but sometimes by the learning rule.
No, always by the learning rule. I do a
Plus
perturbation.
noise.
No, I do a perturbation, and that perturbation either helps or doesn't help. Okay? And I choose the least worst option, essentially. So I undo or I keep that perturbation. But if the perturbation has taken me really far, so say I want to get to the minimum, I jump across, the best I can do is go back where I was.
Ah, yeah.
So I will get some kind of noise. And you can add noise as well. Anyway, all of this says, if you believe what I've said so far, that we can say that for any synapse that's learning, we can summarize its change in some interval as the change that's parallel to the gradient, the good stuff, and everything else. We can just do an orthogonal decomposition. So that looks like this. Here's our weights. In an interval t, we learned. What does that mean? It means we went in, a component of this average change was in negative of the gradient of f. And then we didn't follow this perfectly, so then there's some component which is everything else. Okay? So that's our average weight change. And what it means is, over any time interval t, we can express the total weight change as some component in the direction of decreasing the error, and some orthogonal component that's not helpful. Okay? So we referred to this as task relevant and task irrelevant plasticity, but generally this is useful from the point of view now of say doing a simulation, because we can choose any quality of learning rule we want. All we need to do is each time step take a step in direction of the gradient, and now choose some random vector that has zero correlation with the gradient and add it to the synapse. And depending on the relative magnitude of gamma 1, gamma 2, we get the best learning rules and the worst ones in some continuum. Okay? So, that's a long way of saying that to consider all learning rules in some sense to first order, we can do gradient descent, and then we will just add this irrelevant term to our gradient step. Okay? So that gives us a parameterization of noisy learning rules. So what about this other term, intrinsic synaptic noise? So we didn't mention that just yet. What's this? Well, here we're assuming that this trajectory occurred because, in a sense, some deterministic process plus something which basically doesn't scale with the network size, right? It's some perturbation that has some scaling that's always relative to the gradient, okay? So it's relative to the absolute magnitude of the vector of all weights. But if we let each weight have a noise component that's independent of other weights, and we consider the contribution as n increases, what we have is a random walk, okay? And the expected distance that we move in a random walk is the square root of time, right? And sorry, it's the square root of the number of components in this random walk, okay? So if we now have intrinsic noise, it contributes a term that looks like this, okay? The independent nature of all of these perturbations across each synapse means that this noise component is going to grow with the size of the network, which could be a problem, okay? So, keep that in mind. We're going to come back to that later. Okay, so we've got our learning rules. We've got some way of modeling these two different kinds of noise. Now we want to say, okay, well, what's this task? We want a very, very general task. So we'd like to consider all possible tasks. Again, how are we going to do that? Well, let's consider all possible tasks that a network could solve. Here's a nice way to do this. This is called the student-teacher network framework, okay? And in this part of the investigation, we restrict just to arbitrary feed-forward nonlinear networks. And they're nice because essentially they compute some arbitrary nonlinear mapping from the inputs to the outputs, okay? So we take a teacher network, we call it a teacher network, and we will just make some random weights and fix them. And this gives us a mapping from an input vector to an output vector, a nonlinear mapping. And we can enumerate all possible nonlinear mappings that a network of a given size can do just by randomly drawing teacher networks. And now for the student, we will begin considering only students that have at least as many neurons and connections as the teacher, okay? If we make a teacher network with the exact connectivity but change the weights, then we know that there is a combination of weights that can solve the task, by definition. And now the task of the student network is to find either, well, it won't find necessarily that unique combination, but it should be able to approximate the task arbitrarily. So the students will always have weights that are variable, that are plastic, okay? And from this, on each learning iteration, we have inputs, outputs, inputs and outputs. We compute a difference between these things. This gives an error. It's just a scalar error function. We pass this through our noise-corrupted gradient descent, which parameterizes all qualities of learning rules. And now we study learning performance in this network. Okay? This is the main finding of all of this part here. So if you want to go to sleep after this, that's okay. It's quite hot. Okay. So what happens when we do this? Here is a learning curve. This is the error decreasing over time of a network with 145 synapses that was trying to approximate the function of some teacher network with the same number of synapses. Okay? And it learns and then reaches some steady state performance. And this is with a learning rule that's not perfect. If it was gradient descent, it could probably get to 0. Okay? But it's noisy gradient descent, so it doesn't. Okay? So now, here's the question. What happens if we take a teacher network, fix the size, now take a student network and just add synapses and neurons to the inside of this network, not to the inputs, not to the outputs, but add redundant connectivity, okay? So here's our inputs, our outputs. We're just going to add this thing. And we know that this neuron is not necessary. What happens is if we start adding redundant neurons and connections, we get faster learning and lower steady state error. Same quality of learning rule, same amount of noise in the learning rule. If we make the network even bigger, we learn even faster and get to even better performance. Same quality of learning rule, same amount of noise, just adding redundant connections, okay? And this is a summary of the steady state error as a function of the network size, okay? So this first one was the size of the teacher network, and everything else is a bigger and bigger student, which despite all these distractions coming from the noise is somehow able to learn the function better, okay?
And so you don't have synaptic noise at this point? Right?
No, no. We just have learning rule noise. So now the question is, what happens, so no intrinsic noise, what happens now if in addition we start adding intrinsic noise? And this is why you need to keep in your head this thing I showed earlier, that the noise scales with n. With intrinsic noise, again, the small network learns okay. A bigger network learns faster and gets to lower error, but an even bigger network now starts doing worse. Okay? So here's a summary, and you can kind of see that we get not so good learning, and then as the network gets bigger, it starts getting worse. Okay? So there's an optimal size of neural network if there's some amount of intrinsic noise. Okay?
Tim, do you know what's happening in these two in the middle that have huge variance and
numerical issues? This is very, very messy too. Okay. You have to do many iterations to see this, because this is something on the mean. Yeah, this is just numerics. Okay, so in summary, with an imperfect learning rule, larger networks learn a fixed task of fixed complexity faster and to higher steady state accuracy, on average, right? This is all in expectation. But if you add intrinsic noise, the learning performance eventually diminishes. So there's some sweet spot for the size of the network, okay?
So the way in which you add noise, so the scaling parameter,
yeah,
you don't put the scale parameter explicitly.
No, you just add an IID variable to your...
But the explanation comes from this.
Yeah, the analysis comes from that, yeah.
Okay.
So we can go into the analysis now. So
And the noise is
IID Gaussian noise.
Gaussian, so it's
Yeah.
not possible to have negative and
No, I mean, if you wanted to change this network so it looks a little bit more biological, then you could do that. But we're just taking something kind of standard, vanilla. We don't think that that kind of detail would change the picture much at all, because the analysis actually doesn't
It looks
assume
to
that
me
too much.
that as you increase network size, you increase some kind of a law of large numbers thing, so you increase some size of noise.
That's exactly what's happening. Yes,
Pretty much the explanation.
that's exactly it.
So
Yes.
the type of noise is very important.
No, what's important is the IID nature of the noise. So I can change my I can change my distribution. I could say not Gaussian, uniform, not Gaussian, positive with a skew. The point is, the noise in synapse 1 has zero correlation with the noise in synapse 2. Anything where they share the correlation is something more like the learning rule noise. And as long as they have any amount of this decorrelated noise, and as long as it's roughly the same magnitude for any synapse, you get this. Yeah. Okay, so what's going on here? Can we understand what's happening? So the first question is, why is the learning hard when we have an imperfect learning rule, or any learning rule that's actually trying to follow a gradient? Let's do a little bit of math. So we'll write our error at time t as some multiplicative factor of our error at time t0. If we're learning, k should be positive, okay? But not so big that we go negative the other way, all right? Okay? So we can call k in this case our learning rate. And if k was fixed and small, this would give us geometric learning. And in fact, we would, and you kind of see that approximately. You see a sort of exponential learning profile. But what this allows us to do now is to write k using just a Taylor expansion in terms of the error function and derivatives of the error function. And we've rearranged things a little bit just to collect some terms that we care about. And we've said, okay, terms depending in t squared and higher will require the third derivative of the gradient, third derivative of the error function and higher. And we don't believe that learning, in fact, we don't believe that learning can explicitly calculate this, let alone second derivatives, and certainly not third derivatives. So we're assuming that all of this stuff will appear as some kind of noisy disturbance to this. Okay? And we call this thing here, well, if you're interested in the mathematics, this has to be expanded out, and it's essentially the average correlation of our weight trajectory with the Hessian of the error function. Okay, so why have I written this horrible formula? The point is, k needs to be positive, okay? We've said that if we've got a learning rule that's any good, this correlation should be negative on average, okay? So this thing's negative, this is negative. If we had no curvature, we're learning, okay? This is positive. However, what's in the bracket can change sign if this thing is big enough. If the value of this exceeds the value of this on average, learning stops. Okay? So an immediate prediction of this formula, and this is actually not for a small t. We don't even assume that t is small in this case. T could be big. A way of testing whether this is a valid formula is to say, let's compute k explicitly. We can do that because we know our weight trajectories. We actually know f. Okay? And we can compute all these other things in a simulation. And what this analysis says is that learning should stop when when these two terms balance. Okay? And we call this term, the thing that's causing the problem and maybe getting big, the local task difficulty. Right? It's coming from the curvature. And in fact, you can verify that local task difficulty, we can explicitly compute a kind of critical value of it where it's now going to balance this term, and indeed we see that the learning stops precisely when these two things balance. So that's in a linear network, aka a matrix, right? not very exciting. Linear, a matrix with a quadratic error function. In a nonlinear network as well, yeah, it's not perfect. Here's the prediction, and you know, it's sort of close. And from this analysis, we can actually pull out an empirical K and a predicted K. In the case of the linear network with low and high noise, these on average are precise. And then in the nonlinear network, what we see is that the prediction is somewhat conservative. In other words, all this stuff is only hurting us. The stuff that's third order or higher in the error function is contributing essentially a noise or a nuisance term. Okay, so in summary, and this should not be a surprise to anyone who's done optimization or used Newton's method or anything like that, high positive error surface curvature relative to the gradient, because we pulled out a gradient term here, is what makes learning difficult. Okay? Here's a picture. Okay? So we're trying to get down this bowl, and we're here. So what do? We look at the gradient, and it tells us go this way. And we take a step. But how big a step do we take? We don't know. If that step was big, then we end up on the wrong side of this thing, and then we maybe start buzzing around. Okay? So clearly, this is an example where the more curvature we have, the harder this thing is to learn. Okay? How can we quantify explicitly the effect of the curvature or the second derivative? It's not exactly the curvature on learning. Well, here's the picture. If we're at a state where we've learned a bit, we're not completely useless at the task, then by definition, we're in a region of positive curvature, where the Hessian is positive, semi-definite maybe. So what that means is if we now perturb our weight, the expected benefit of this weight perturbation is negative. The error is generically going to be higher. Okay? If we think of this in many dimensions, what this means is that there's some kind of bowl. We want to get to the bottom of the bowl, and for a generic perturbation, on average, there's going to be some kind of penalty. Okay? And a way to compute that penalty is to think of the second derivative, the Hessian matrix, and the Hessian matrix can be decomposed or can be re-expressed as by a singular value decomposition or something similar, where we can describe the transformation that the Hessian performs on this weight perturbation as being summarized by the size of the eigenvalues. Okay, the relative size of the eigenvalues of the Hessian will tell us how far this random perturbation moves us. What's the average value of the eigenvalues of a Hessian? Well, if we're near the bottom of an error surface, a Hessian is positive definite. We can diagonalize it, and that means, well, that's one bit of the intuition, but the point is it's going to be similar to a diagonal matrix. Trace is invariant under a similarity transformation, and that means we can just take the trace of the Hessian, and that is the sum of the eigenvalues. And the average eigenvalue is this quantity divided by the dimension of the matrix. Okay? So this is a long way of saying that the average penalty for a random perturbation when we have curvature is equal to the average eigenvalue of the Hessian of this function. Okay. So we know now why learning is hard, at least in this sort of simplified framework. The thing that's hurting us is the curvature. So what can we do? We could slow down, or we could alter the learning rule. Sorry, we could build a term in that knows where the curvature lives, essentially follows the downward directions and avoids the very curvy directions. But we don't even think the brain can compute gradients. Certainly can't compute second derivatives. So that doesn't seem biologically plausible. We could decrease the learning rate as we start to encounter high curvature regions. So as we start getting better, we learn slower. But then we'll learn slower. We could just decrease the noise, and that would be wonderful. If we could make perfect synapses, We would, but we can't because we're made from biological components. Or, why don't we just reduce the curvature of the task? Okay? This thing that's getting in our way is just the curvature of the error function. If we could somehow make the error function less curved, many of these problems would go away. How can we do that? This is the main insight of this analysis. When we do this network resizing, we are by definition taking a fixed mapping, and we're now representing that mapping redundantly. We're adding more neurons and synapses than we need. So what this is like taking an error function from Rn to R, it's a scalar error function, and lifting it to a higher dimensional space, n tilde, where n tilde is bigger than n. So we're taking our same task, and we're going up and adding redundancy and going into a higher dimensional space. Okay? So we're just embedding our error function. And then, you could also think of projecting down. Okay? And if we think now of this projection operator, wave our hands a little bit. In the linear case, this is all precise. In the nonlinear case, it's a mess. And it's not something I'm capable of solving. My postdoc did that bit. You can do some calculations which essentially show how the gradient should scale depending on the redundancy of this embedding map. So this embedding map is something like a projection followed by a rotation. So it's a semi-orthogonal transformation. What that means is it has n eigenvalues 1 and n tilde minus n 0 eigenvalues. Okay? And what that does to the Hessian is written as follows. And the point is that the gradient is going to grow with n, but the Hessian, because it was based on this task, which we haven't changed, doesn't change. Okay? And this precisely says that the scaling of the Hessian is favorable with respect to the gradient if we just add redundancy in the right way. Okay? So a way of saying this is just adding excess redundant neurons and synapses flattens out this surface relative to the gradient. Okay? Next question is, okay, we've done this weird thing where we just add redundancy. And I argued at the first part of the talk that there is evidence for redundancy because this bit of the brain that represents tasks for some reason keeps finding different ways of representing the same task. So yeah, there's probably redundancy. We can also see this redundancy at yeah?
For going there. So this explanation would explain why you learn better, but
yes.
not faster.
Actually, the two are the same because it gives us the value of k not only determines, so it gives us the steady state and the rate. Okay. The two things are related. Yeah. Okay. So there's some evidence that the representation is redundant, but there's also anatomical evidence that the circuitry of the brain is redundant. At the macro scale, you can see lots of these kind of parallel connections. But even at the micro scale, you see really weird things like this. So this is a part of the brain. So I think this is hippocampus, and this is hippocampus, and this is cortex. Here's an axon, and here's a postsynaptic dendrite, and it's making two synapses on the same cell. And if these two synapses can, in some sense, learn somewhat independently, this is truly a redundant connection. And here's something else very similar. That's the same case here, and this is now two different release sites with the same postsynaptic cell. And these things are very common. And in fact, it depends on the part of the brain that you look at, but some of them you see many, so something like 30% of synapses have this weird redundancy in it.
At the same time, like in the retina you have stuff like this,
yeah.
But usually they release different stuff.
Yeah, here I don't think that's the case.
Okay.
Yeah, so this certainly is a glutamatergic synapse, and it'd be very surprising if this axon was releasing two different things at this site and this site there when they're at 1 micron.
Okay.
So, yeah.
I was calling the retina is another release glutamate and GABA at the same time.
Yeah.
But you're asking independence from the synaptic context. in the sense that...
No, not for learning, no. For learning, they can be correlation. The noise is independent. And actually, that's the bit I haven't yet got to. So, adding these redundant connections flattens out the surface relative to its gradient. And that's good. But if each of these connections contributes an independent noise source, then the good bit is balanced by a bit of badness, okay? And at some point, for a big enough network and for a fixed complexity of task, is not going to help. We're only going to hurt ourselves, and in fact, do worse. And this leads to an optimal size of network, and there's a formula here you can compute, and actually the formula gives you a bit of insight. So n star here is the optimal network size. This is an implicit formula, annoyingly. N is the size of the teacher network, which you can think of as task complexity. More complex task, bigger network. That makes sense. Longer interval between receiving feedback on error, I need a bigger network to buffer that. Stronger gradient relative to my task irrelevant network, it helps to be bigger. If, however, the intrinsic noise is big, then now I have a problem. So this is the one that kills me in the end. And you can check whether this formula works, and it does. The linear case is kind of just a sort of toy example, but we can compute the optimal size. So now we have a noisy learning rule, but we also have intrinsic noise, and we increase the amount of intrinsic noise. And with very high intrinsic noise, we see a strong penalty for adding these synapses. But certainly it helps to make a network that's a bit bigger than the teacher if the learning rule is not perfect. And the same is true now for the nonlinear network, with different scaling. And the interesting thing is that actually the scaling doesn't seem as bad in the nonlinear case. And we need to do a little bit more work to sort of understand that in more detail. But that's maybe good news for the biological nervous system, is that maybe the intrinsic noise, it hurts you, but maybe not so much that you can't have a kind of big neural circuit and get a learning benefit from it. Okay, so that's it. That's everything I have to say. I'm just going to put the summary points up very quickly. So I hope I convince you that the neural representations seem to be degenerate. And this, interestingly, means that the representation of a learned task can drift over time. And I think there's interesting philosophical connotations to this, and practical ones. A simple error feedback means that this issue is maybe not catastrophic for understanding how the brain works. If we're learning a task of fixed complexity, and this is the point, and we add redundancy, the learning is easier and quicker in the larger network, and the reason is that we have this degeneracy. We're adding zero eigenvalues to a Hessian, essentially. But just making stuff degenerate doesn't always help. If every time you add a synapse you add a bit of noise, the noise wins in the end. And that means that there's probably some optimal size for most networks where just adding neurons and connections doesn't always help. So with that, thank you for listening. Dhruva Raman is the person who did the heavy work in analyzing noise. He has a control theory background, so he put his control and optimization talents to work here. This was a nice example of that. Adriana helped with the linear model analysis and using data provided by Chris Harvey's lab in Harvard and gathered by Laura Driscoll, who's now at Stanford. And I'd like to thank Alessio for inviting me, funding, and all of you for paying attention. Okay.
So, just a comment on perhaps a different interpretation of why you could eliminate some of the noise in a biological network. So, I don't think, based on recordings from thalamus to striatum, thalamus to cortex, cortex to striatum, of synaptic plasticity in the short term. So you stimulate repeatedly with, say, 20 hertz, and you look at the postsynaptic currents.
Mhm.
in voltage clock mode, for example, and then you see that there's a bunch of noise, but that noise is never uncorrelated.
Mhm.
Precisely because of the axon collaterals and
Yep.
all kinds of phenomena
Yeah.
you just described. So, but yet you see that there's this degeneracy that you're referring to can be thought of in plainer terms as simply that if you set up a network in which you think of zeros and ones, there is never anything close to the end combinations of the different patterns that you see.
Mhm.
And the reason is that those patterns imply other patterns in return. So there's two levels of non-correlated activity you have. One that has to do with who talks to whom,
Yeah.
and that induces correlations. And the
Yeah.
second one is that given that you've talked to whom, what gets back to you?
What do you do with that information? Yes.
Now, where biologically, the comment is, sorry for the long look, but where biologically this could be implemented could be in an integration process from all the synapses. So even though you may have a bunch of noise that you could call synaptic, etc., the point of having all that noise coming into the dendrites is perhaps that your dendrites are still going to filter a bunch of stuff like that. In the end, you end up seeing the zeros and the ones, which is what people that do system physiology.
Yeah. So this another way of saying this is if I understand, is that I may have multiple release sites and multiple contacts because it makes sense to take an average because each contact is not that reliable. Absolutely. Yes.
Even if
So,
it's a nonlinear average,
yeah.
it's an average.
Yeah. So that's absolutely true. And actually, the analysis here, actually, part of it captures that because the oops, in this formula, let's see. This formula says it pays to have redundancy if you can think of T, this intermittency in the feedback, as a bit of noise in communication of task performance, etc. So some of that noise could be because I don't get very reliable transmission through my synapses. And what this is saying is that if that's the case, make a bigger network, and possibly part of the benefit of the network is that it's doing some averaging as well.
It's finding a
Yeah.
calculation effect kind of thing.
It's interpolating stuff that, so we didn't really focus on this. What this is quantifying is the information bandwidth that's coming into the circuit. And it's saying, if you've got low bandwidth, make a bigger circuit. And my interpretation of that is what you're saying is that do average across some unreliable data points or something like that, or unreliable signals.
Some percolation. You're allowing different pathways to open up for you.
Yes. Yes.
And you still keep just a few elements in the pathways, no matter what.
Yeah.
So then, with more pathways to choose from.
Yes.
And the question would be, so that was the question that I had from the beginning.
Okay. Which is a bigger, yeah.
Learn,
Okay.
which happens. It's not just one task. It's usually.
Yeah. Okay. Okay. So that's actually another interesting point. We only talked about one task. And
maybe related to Marco's question.
Yeah.
Would be can the network, once it learns the task and it gets to a steadier, could the same network learn something else?
Good. Okay. Two ways to think about this. I can make an F that describes my performance on all tasks. So if I have multiple tasks that my network's supposed to solve, the simple answer is, well, that just changes the F. And then same story. Another way to look at it is to say, well, I could have one F. And then maybe there's some other thing which I don't want to think of as like an error function. Maybe there's some biological constraint. Maybe the circuit wants to control its average level of activity, for example, just because you don't want your brain to explode, something like that. That's a constraint, right? And it's a constraint which doesn't necessarily help you learn. There's no reason for that constraint to help you descend your error surface. Instead, it's going to be doing something here. So we've been treating this thing as a stochastic term. It doesn't have to be. There could be a deterministic component in this term, which, for whatever reason, does not correlate with the gradient with respect to the task you're talking about. And two different tasks could have that flavor. Doing task A, being good at task A might not make me any better at being at task B. It may even hurt me. So from the perspective of task A, all of that stuff is this annoying perturbation which is correlated across the synapses. It's not IID noise. They're all kind of trying to solve this other thing which is getting in the way, and that's why it would go into that term as well. So you could interpret things that way. But we again, it'd be nice to explicitly to maybe cook up an example where we have one task where being good at that means you have to be not so good at the other one, and see whether this analysis is actually helpful for understanding that.
Make the larger f somehow dependent on time, like you
you switch your f's. Yes,
like
yeah.
Yeah, because that's the only. I usually think in biophysics.
Yeah.
So in the beginning, I was like, well, biophysics don't agree with this kind of stuff, but at the bigger level, at the larger level with the system, then the question about whether or not one learning task and then the mechanisms that can drift down to something that looks like an average in the end, raise an eyebrow until you consider, for example, that there's all this stuff that is fashionable right now, AI, right? What you have is a bunch of F's sort of tangled on one another with what people call tensors, which is just a higher dimensional matrix, right? But what happens with biological brains is usually that you do one thing and then another, perhaps two things, but no more, right? And then there's a lion, then you drop everything because you do another thing, which is run away.
Yeah.
And what baffles us as humans is that a computer is capable of doing all these things that we don't seem to be able to do all at once.
Yeah. But that's not how the biology does it. Yes.
Yes, we do it. Anyway.
Yes. So another thing is to say that this model, I mean, is not the whole brain. This is one circuit.
Exactly.
And my belief as a biologist is the reason we have different bits of brain that have very different structure and shape, active in different ways, have different neurotransmitters and so on, is precisely because it's not necessarily a good idea to have this big general purpose spaghetti where it learns everything you ever need to know and it's in some weird no, it makes more sense to compartmentalize. And in fact, if it's true that the noisiness kills you in the end, partly this hints at saying that actually if I've got task involving like different sensory modalities, hearing, seeing, etc., I could make a giant spaghetti to do everything, but maybe that one gets hurt by the intrinsic noise. Maybe it makes more sense to make different sub-networks that are only computing an F that's relevant to what they're doing and not mixing them. And I think depending on the brain area, you're going to see different levels of mixing and different levels of what they call mixed selectivity and all of this kind of stuff as well. So I think you can sort of see the kind of, this is extremely simplified, but you can kind of see where those different issues can pop up just by this quite boring equation, I think.
When you were looking at the initial experimental data, so there's a learning period, and then you measure how the rat. There's a point when the rat knows a maze, knows the patterns, so it's pretty much steady state. Yeah.
So we're here.
So
and maybe this guy was learning a bit still.
Then there is this restructuring.
Yes. Yes.
But is it by any measure getting more efficient at the task?
Not in the behavior, right?
Yeah.
But maybe there's some more subtle. Yeah. So this is essentially a very crude readout. It's a binary readout. Did it turn the right direction or not? but maybe it walked more elegantly down the maze, or did something.
It takes less time to take the decision.
Exactly.
No, it doesn't.
Less effort.
So those things are not. Those don't change.
Okay.
So to the resolution of measuring the behavior, there's no obvious improvement, efficiency.
And maybe think of it like driving.
Yeah.
Like, maybe I won't get there faster, but I don't have to think as much as.
Yeah. And I think that might manifest this naively. That would manifest itself as saying that actually, on average, fewer neurons are active.
Yeah.
But that's something we don't see in the PPC. So it's the same number of neurons that roughly are getting excited in the entire. It would be very cool if instead what we saw was at the beginning. And in fact, maybe if we get the learning data, what we'll see is that during learning, we have many, many more neurons that are active. Or maybe this neuron is not only active at the beginning, it's active here as well.
Yeah,
And then gradually we get a refinement of this relationship.
the activation is
Less organized, yeah. That's what I think, that makes sense, I think.
Do you analyze the errors?
There's hardly any errors in this, yeah. So, and again, that's why...
after the training, right?
Yeah, so there are some error trials, but there's not enough data to say anything interesting about the dynamics in the network. So that's why we need the learning phase and the steady state, yeah.
Because it's not so easy to find reward signals in this kind of areas, at least in my opinion. So
Not behavioral reward signals. I mean, you could say that every time the animal's thirsty and it needs a drink, so it's getting a reward. And following the discussion earlier, every step that the animal takes, in a way, part of its brain is making a prediction about what the visual cortex should see, etc. And sometimes it's going to get those wrong, sometimes it'll get it right. So my view is that it's always seeing some kind of error feedback, but maybe not something that's detectable as a big burst of dopamine or something like that. Then there should be this small error signal all the time. Otherwise, I don't know how.
perhaps in some special areas there are some, I don't know, it's a question that we have at this moment, but at least not in all the areas in the monkey. You see that in most of the areas.
But that could be a measurement problem.
Exactly.
Yeah.
Because anatomically, you have the medial frontal bundle reaches pretty much everywhere in cortex,
Yeah.
primates,
Yes.
rodents, and
Yes. Yeah. So everyone's getting a little bit of a hint.
and it's tonic,
Right.
and it's distributed every 300 microns. You have,
Yeah.
10 nanomolar
Yes.
concentrations on average, unless chocolate or sex
Yeah.
content.
Something big happens, then you have a serious change. But I think this kind of background tone of modulation might be the error signal that we're employing exists.
So, as Roman is saying, the problem is that you wouldn't be able to find it.
Maybe not.
What you were saying, I don't know. Because if you're looking at it physiologically, all you
Yeah.
have is firing rates.
Yes. Not only that, each synapse might be getting a slightly different
Exactly.
error signal at different point in time. So yeah.
And
Yeah.
the calcium imaging either, it's even worse because you have resolution issue.
Yes. Yeah. Yeah.
Question
Fernando.
about this part also.
Yeah.
So you did some linear fitting between the physical variables and
Yeah.
and you show that this fitting changes with time, right?
Ah, yeah. Sorry. So
And then you compared it with some other fitting that holds for all time.
yeah, this thing.
If I understood correctly, the green one.
Yeah.
You did it with a neural network. Perhaps?
No. Same procedures.
It's also
Least squares.
Least squares.
Least squares, but taking the same quantity of data points, but necessarily fewer data points per day.
Okay.
So that might also explain, because we didn't want to just give this one more data and get and overfit. This was simply to say if we have a bit of data from each day, can we find some sort of
Or if you perform an average for each day.
yeah
That data set to do.
yeah something like that. Yeah.
Is this network all synaptic?
So
Can you add
this
some non-synaptic modulator.
Yeah, so this thing, the adaptive neuron, needs a modulator. It needs an error signal. Otherwise, these synapses don't know what to do. So I haven't shown it here, but it's kind of like we've got these weights, and the weights receive two things that tell them what to do. They depend on their previous value in time, and then they also depend on the discrepancy between this and the prediction and the measurement. So that error signal is fed back to adjust these. And when you do that, you do much better than just keeping a static neuron. I want to use the word neuron in cartoon sense. Yeah. Yeah.
Okay, if there are no more questions, we can thank again Tim for.
Thank you, everyone.